Hi there, my name is Roberto A Colon. I'm an undergraduate in aerospace engineering at Purdue University, and this summer I worked at the Plasma Dynamics and Electric Propulsion Laboratory at the University of Michigan on a project titled Developing a High-Speed Reciprocating Probe for Hall Thruster Plasma Investigations. During this presentation, I'll be explaining how we've developed a tool that can aid in the process of getting data from the plasma and the plume of a Hall thruster. But first of all, I'm going to give you a little background of what a Hall thruster is. A Hall thruster is an electric propulsion device that is mainly used for satellite station keeping. The way this thruster works is it makes use of an electric field and a magnetic field to produce thrust. The way that the electric field works is that we have electrons coming from the cathode towards the anode. Those electrons get trapped in the magnetic field, and the electrons are going to rotate along the channel of the thruster in the E cross B direction. Those electrons that stay rotating along the channel of the thruster are going to be used to ionize a propellant that's going to come from the back of the thruster. Once the propellant is ionized, it's going to be turned into a plasma, and that plasma will be accelerated by the electric field to produce thrust. The plasma that we see coming out of the thruster on the upper left image in this slide is the topic of our investigation. Now I'm going to show you what we currently use, what we used in the past to explore this plasma. The Hardborn 1.0 is just a reciprocating machine that just goes back and forward. The probe, right now we just install a probe on top of this device, and we send the probe in and out of the electric propulsion device that you saw in the previous slide. The purpose of this device is to minimize the time that the probe spends in that plasma region. The probe basically measures characteristics of the electrons that are found in the plasma and other important data of the plasma. The device currently underwent a full upgrade, and that's what I will be talking to you about. Some of the problems that this device had and we tried to address this summer were the following. The hardware was not fully protected from the plasma plume. As you could see from the previous picture, we just had the reciprocating device, but we didn't really have any enclosure to protect it from the harsh plasma environment that's at very high temperatures. Another problem that we had was the data acquisition system that was inside the controller was very slow. We were only able to get 20 points per second, which is really slow for the applications that we were investigating. Another problem that we had was the resolution of the position feedback that we were getting was really poor. We were getting very noisy data, and we weren't really able to identify the position accurately. Another problem, which is one of the main problems, is that the amount of time that the probe was spending in the plasma was too long, and that was causing damage to the probe, and we weren't really able to get a good set of data just because we were destroying the probe instead of going in there and investigating the plasma. And finally, we didn't really have a good control interface for the user. The user wasn't able to input how much velocity he wanted from the device or how fast he wanted to go in and out. So we tried to develop a system that a user interface that would let the user choose all of these things before actually sending the probe into the Hall thruster. So the way we addressed these issues was I designed and built an enclosure to protect the heart from the harsh environment. I accelerated the data acquisition processes by manipulating the commands that were available in this controller. Significantly improved the resolution of the position feedback so that we can get more accurate position data. We minimize the time that the probe spends in the harsh plasma environment. As I said, that was one of the major problems. And a final thing was to improve the user interface, as I explained before. Now I'm going to talk to you about the new design that I developed this summer. The hard enclosure, as you can see from these pictures, fully protects the device and keeps it protected from the harsh plasma environment. Another benefit of this enclosure is that its robust design makes it portable, so we can get this device in and out of the vacuum chamber, which is where we test our thrusters, and it is easy to move around. The plates that you see on top of the structure on the bottom left picture are made of graphite. So these graphite plates are able to withstand very high temperatures, which protects the device from the harsh plasma environment. And the plates slide in and out from the structure. So whenever we need to test, whenever we need to make an experiment inside the chamber, we can just slide these in, and when we're out of the chamber making improvements to the device, we can just slide them out, and it's very convenient. As I said, the data acquisition was one of the major problems as well. The way we addressed that was by manipulating the commands that were inside the controller. I took the time to learn the language that is used to program inside this controller and discover a lot of commands and functions that could be used to do this process faster. So the way I did it was I triggered the data acquisition internally at the same time that the motion of the device started. I gave the user the ability to control the period and the amount of points that we get from the motion. So instead of just saying that we're going to get data every millisecond, the user can say that he wants to get data every 0.05 milliseconds. So the user has the liberty of choosing now. And instead of having the analog signal that we had before with very poor resolution, I found a way to output the position feedback digitally. So now the user has the option of doing that and saving it to a file inside the controller instead of having to figure out what the position is from a very noisy set of data. The linear motion of the device was also improved. As I said, we needed to make it faster so that the probe will get in and out of the harsh plasma environment as fast as possible. My approach to this was to find a command and a function that would allow me to have a linear trajectory, have the device have a linear trajectory instead of the more parabolic trajectory that we had before. This command or function allowed me to input the distance that I wanted to go into the plasma thruster and the time that I wanted that motion to be accomplished in, as opposed to the previous approach that we actually determine the distance, velocity, and acceleration. By just determining the distance and the time, the program optimizes the velocity and acceleration that is necessary to carry out this linear trajectory. As you can see from the images at the bottom, the bottom left image shows the trajectory that the new system has. As you can see from the red part is the part that the device actually spends in the plasma, and it's very little compared to how it was before. Like before, you had a relatively flat region, and the probe would just stay there and receive all this heat and whole current acceleration that just destroyed it. Now we just come in and out, and with minimum exposure to the plasma. In addition to the data acquisition system that we had before, I added, at the same time that this motion starts, I added an external trigger. So what this would do is that when the device starts moving, there will be a trigger that would go out of the system, and would what the function of that trigger is that it would activate all the other data acquisition systems that we use in the lab during a whole thruster experiment. So for example, once the trigger comes out, it would activate the high-speed camera. It would activate other data acquisition systems that record things such as current, voltage, and things like that. Here's a closer look of that upper region that I told you was the region that the probe actually spends inside the plasma. The hard 1.0, which was the previous design, I calculated that the amount of time spent was 60 milliseconds, which seems pretty small, but for the applications that we're using it, every millisecond counts. And now with the improvements that I made with the linear trajectory, the the time spent in the thruster actually went down to 15 milliseconds. So that's a 75% reduction of time spent in the thruster, which is going to be it's going to be very, very important for future experiments in the laboratory, and it also expands the capabilities of the laboratory. As I said, one of the problems that we had was that the user had trouble controlling the system. Like he had to create a program and then run it, but he didn't have the option of changing settings while testing the device. So here, as you can see from the image here, this is what the user, what the front panel of the control device would look like for the user. As you can see, he could input distance, speed, acceleration. For data acquisition purposes, he can put how many points he wants to get, and the period. The period, I managed to get it down to 20 points per millisecond. Before, it was 20 points per second, so that's a significant improvement. The resolution of our data is going to be way better now that we have that high resolution. And as you can see on the bottom, the user can select where to put that text file. He no longer has to get the analog data out and analyze it. The digital feedback just goes straight to the file and the controller. And to the right, we have a plot of the trajectory that the probe had when it went in and out of the whole thruster. This trajectory gets plotted out seconds after the motion actually happens. One thing that you can see here is that speed and acceleration are still inputs. This is because if the user doesn't want to use the linear trajectory option that I explained before, that minimizes the time spent in the plasma, he still have the choice to choose speed and acceleration, because that's something that sometimes the user wants to have. This interface that you see here was the result of implementing the AeroBasic code, which is the code that was created inside the controller, to LabVIEW, which is a more user-friendly system that is used in other systems in the laboratory. For now, we've pretty much gotten the system to work and accomplish oral goals for the summer. We made the system faster, getting in and out of the plasma faster. We reduced the time spent in the plasma. We got a digital output, so we don't no longer have the hassle of having to figure out what we get from the analog signal. We built an enclosure to protect the device, and we built a user interface to make it more user-friendly. For the future, one of the things that needs to get done, we need to test the device inside the large vacuum test facility, which is where we make all experiments. The device has only been tested outside and at ambient pressure, and we think that by testing it inside a vacuum environment, there will be changes in the way the motion happens. So we need to quantify those differences and adjust the device so that it works optimally in that environment. Another thing that needs to be done is the probe installation. Right now, we just have the device and the structure around it, the enclosure that I built, but we still haven't built a probe that will go on top of the device, which is what actually measures the electron and plasma data that I talked about before. So we need to build that and install on top of the device. And once we do that, we need to see how the weight of that probe and the momentum that it gives to the device. We need to quantify that and adjust the system accordingly. We're probably going to have to adjust the gains of the controller inside the system so that it takes that new weight into consideration. So that's basically the work that I did for the summer. In the future, I plan to come back, hopefully as a graduate student, to the Plasma Dynamics and Electropropulsion Lab and keep doing work on Hall thruster devices. Thank you.